In this video, we'll see three things. So today agenda is first, what are the essential things we require in order to have a proper communication between two entities. The second thing, how the evolution of internet has been taken place, that is the evolution of internet. And the last one is OSI model, which is responsible for transferring the data between the two entities. So the very first one, what is the communication? So what are the five basic entities that require in order to have a proper communication? So as we all know that in order to have any communication, minimum we require two things. One is sender and another one is receiver. So other than this, what we require? We require the data that need to be communicated between the sender and receiver. So the sender is ready, the receiver is ready, and the data is also ready. So what we need? We need some sort of medium in order to transfer that particular data. So that is nothing but your transmission media. So it may be a telephone line, it may be a coaxial cable, or it may be a twisted pair or fiber optics, anything you can use. So other than these four, we need one more important thing that is called as protocol. So you have everything. You have a sender, you have a receiver, you have the data to transfer, and you have a proper media to transfer. But everything is there. If it doesn't follow any certain rules and regulations to transfer the data, then obviously the data will get discarded. So in order to avoid that, we need to follow certain protocol to have a proper communication. So these are the five essential things what we require in order to have a proper communication. Now next, move to the next concept, that is evolution of internet. So before going to evolution of internet, just we know simply the definition of a network. What is mean by a network? As we all know, network is nothing but the interconnection of two or more entities, and that entities may be a system or a terminal or a server, whatever may be the case. So that is a network. Now in order to have a proper communication between one network and another network, we need an internet. So without internet, we can't transfer the data from one PC to another PC until and unless it is a local area network. If you move out of the local area network, obviously we need internet, which in turn will call it as a wide area network. So how this internet has been evaluated before internet came into existence, what people used to do in order to send a mail or in order to have a proper communication, we'll see through a video. So just we'll go right. Or we'll open the video with VLC player. Now we'll see.
The Internet in the year 2009. We send emails, make calls over the Internet, and discuss topics we take an interest in. Even our banking is going virtual. But what we take for granted today was only a vague idea 50 years ago. In order to understand how we got this far, let's go back to 1957, when everything began. Before 1957, computers only worked on one task at a time. This is called batch processing. Of course, this was quite ineffective. With computers getting bigger and bigger, they had to be stored in special cooled rooms. But then the developers couldn't work directly on the computers anymore. Specialists had to be called in to connect them. Programming at that time meant a lot of manual work, and the indirect connection to the computers led to a lot of bugs, wasting time and fraying the developers' nerves. The year 1957 marked a big change. A remote connection had to be installed so that the developers could work directly on the computers. At the same time, the idea of time sharing came up. This is the first concept in computer technology to share the processing power of one computer with multiple users. On October 4th in 1957, during the Cold War, the first unmanned satellite Sputnik 1 was sent into orbit by the Soviet Union. The fear of a missile gap emerged. In order to secure America's lead in technology, the US founded the Defense Advanced Research Project Agency in February 1958. At that time, knowledge was only transferred by people. The DARPA planned a large-scale computer network in order to accelerate knowledge transfer and avoid the doubling up of already existing research. This network would become the ARPANET. Furthermore, 3 other concepts were to be developed which are fundamental for the history of the Internet. The concept of a military network by the RAND Corporation in America. The commercial network of the National Physical Laboratory in England. And the scientific network Cyclades in France. The scientific, military, and commercial approaches of these concepts are the foundations for our modern Internet. Let's begin with the ARPANET, the most familiar of these networks. Its development began in 1966. Universities were generally quite cautious about sharing their computers, therefore small computers were put in front of the mainframe. This computer, the interface message processor, took over control of the network activities, while the mainframe was only in charge of the initialization of programs and data files. At the same time, the IMP also served as interface for the mainframe. Since only the IMPs were interconnected in a network, this was also called IMP subnet. For the first connections between the computers, the Network Working Group developed the Network Control Protocol. Later on, the NCP was replaced by the more efficient Transmission Control Protocol. The specific feature of the TCP is the verification of the file transfer. Let's take a short detour to England. Since the NPL network was designed on a commercial basis, a lot of users and file transfer were expected. In order to avoid congestion of the lines, the sent files were divided into smaller packets, which were put together again at the receiver. Packet switching was born. In 1962, American Ferret aircraft discovered middle and long-range missiles in Cuba, which were able to reach the United States. This stoked fear of an atomic conflict. At that time, information systems had a centralized network architecture. To avoid a breakdown during an attack, a decentralized network architecture had to be developed, which, in case of loss of a node, would still be operative. Communication still used to work through radio waves. That would have caused problems in case of an atomic attack. The ionosphere would be affected and the long-wave radio waves wouldn't work anymore. Therefore, they had to use direct waves, which, however, don't have a long range. A better solution was the model of a distributed network. Thus, long distances could be covered with a minimum of interference. Another milestone followed with the development of the French network Cyclades. Since Cyclades had a far smaller budget than ARPANET, and thus also fewer nodes, the focus was laid on the communication with other networks. In this way, the term Internet was born. Moreover, Cyclades' concept went further than ARPA's and the NPLs. During communication between sender and receiver, the computers were not to intervene anymore, but simply serve as a transfer node. Cyclades' protocol went through all machines using a physical layer that was implemented into the hardware, providing a direct connection with the receiver, an end-to-end structure. Inspired by the Cyclades network and driven by the incompatibility between the networks, their connection gained in importance everywhere. The phone companies developed the X.25 protocol, which enabled communication through their servers, in exchange for a monthly basic charge, of course. DARPA's transmission control protocol was to connect the computers through gateways. And the International Organization for Standardization designed the OSI reference model. The innovation of OSI was the attempt to standardize the network from its ends.
So this is all about the evolution of internet. So if you just recollect the points, what are I have shown in the video. So before the existence of internet, long ago in 1957, some batch processing used to be done. Later on, it came into time sharing, and around in 1969, the ARPANET came into existence. Of course, it's been started the work in the for the to develop ARPANET has been started in 1966, but it came into existence in 1969. That is Advanced Research Project Agency. Then after doing some what we say video, there is some commercial networks and the European all these things, and all these things mix up in order to develop a technology, and we came up with a new thing called as an internet. In the video, also in the later part, in the conclusion part, we have seen something called as OSI model. What our next topic to be discussed. He has stretched on OSI model, where we have certain layers and which is responsible in order to have a communication between the sender and the receiver. So now we'll see what is an OSI model and what are different layers present in that, and what are the responsibilities of each and individual layer, and how it helps in order to have a proper communication. Now let's go to the OSI model. So in OSI model, there are total 7 layers. So the first one is something called as physical. The second one called as data link. The third one is network layer. Fourth one, transport layer. The next, presentation layer. Next, session layer, and the last one is application layer. So these are the 7 layers which are present in our OSI model. So what are the data you transfer from one system to another system? That data will go through or passes through all these 7 layers at the sender side and as well as at the receiver side. Now we had a big question over here. As many books and many authors, so many authors said that we require OSI model in order to transfer the data, like what we going discussing now. It need to pass through all the layers, that is physical, data, network, transport, and all these layers. Did ever we thought where this OSI model exists? So this OSI model logically exists in our operating system. What are the operating system we install? By default, logically, this OSI model present in our operating system, and through that operating system, it will make us to communicate with the another system with the help of these layers. So now what we do, we'll discuss individually each and every layer, right? So first what we'll do, we'll discuss the first layer, something called as physical layer. Now, as in the very starting, we discussed the 5 essential things or 5 things that is required to have a proper communication. The one is sender, one is receiver, the third one is data, and the fourth one, which is called as transmission media. That all that physical specifications what we require in order to transfer data, that will be taken care by in your physical layer. For example, the type of cable what we are using, the type of cable what we are using, whether you are using a twisted pair cable, in that again twisted pair you have so many categories, and what is the data rate of that cable. All these things will be considered in your physical layer. Technically, what are the response of physical layer? Technically, if we name them, the very first thing is the data in physical layer is represented in the form of bits, that is 0 bits. So what are the data you send? As we said, the physical layer is nothing but the media what we use. In our media, what is the mode of transmission? what is the mode of data that will be transmitted, in which form. Let us say if it is an analog, it will be in sine wave, and if it is a digital data, it will be represented in zeros and ones. That is what the data will be represented in physical layer, that is in the form of bits. Other than this, or the data rate consideration will also be taken care by your physical layer, and also the topology in which your the topology of your network. Now again here comes a new term, topology. The topology is nothing but the physical structure of how you lay your network. We had different kinds of topologies. If you go in depth the topology, we had a bus topology, we had a star, we had a mesh, we had a ring topologies, 4 to 5 topologies. So in what way, in what physical structure you have laid your network is nothing but your topology. So this also will be taken care by your physical layer. So other than these four, one more is also there, that is nothing but your transmission mode. That is the transmission mode. In transmission mode, as you know, there are two entities. In order to have a communication, the communication need to be happen in one of the three modes. One is simplex, one is half duplex, and another one is full duplex. What happens in simplex mode means there will be only one way communication. That is, the sender always sends data to the receiver, and the receiver always receives the data. There is no option of sending data back to the sender by the receiver. That is the simplex mode, that is one way traffic. If you go ahead with the half duplex mode, there will be two-way communication. That is, the sender can talk with the receiver, and the receiver can talk with the sender. But the thing is here, it is not carried simultaneously. That is, just like what we in olden days, we need to use something called as walkie-talkies or the telephones. What they used to do, they used to talk only one person at a time. Once he finishes his conversation, the other person starts the conversation. That means it is a half duplex communication. So at a time, only one side communication takes place. That will be done in your half duplex mode. And coming to the last one, that is a full duplex mode, where we had both sides, that is a two-way communication, but is simultaneously. What in half duplex mode, only one at a time. Here both we can have an at a time, that is simultaneously, just what we are having the conversations in our mobile phones, today's mobile phones. So these are the different responsibilities of a physical layer in your OSI model. Now we'll move to next layer, that is data link layer. Now, as I said, the data in physical layer is represented in the form of bits. In the same way, the data in data link layer, as the bits have moved to the upper layer. As we see here, the physical layer. After the physical layer, the data will move to data link layer, right? So in data link layer, we'll call the data with a name called as frame. In physical layer, we call it as a bits, and in data link layer, we'll call it as a frame. Nothing new in that. What the data link layer will simply do means, it will add an header and a trailer to the series of bits, that is a sequence of bits, and that makes a frame. So this is one responsibility of what we say the data link layer. And the second one is nothing but your physical addressing. The second responsibility of your data, the other responsibility of your data link layer is physical addressing. So in a network, if you want to identify a system, you need to, not in a network, in order to have a identify a system, we need one address. That is nothing but your physical address. In turn, we'll also call this as a MAC address. This is nothing but your NIC address, which is represented in hexadecimal notation. Very simple, right? Very simple. So the next responsibility of your data link layer is nothing but your flow control. And then we had error control, and the last what we had is something called as access control. In data link layer, we have a mechanism in order to control the flow by synchronizing among the sender and the receiver. And also we do have something called a CRC, that is cyclic redundancy check methods, to control or to rectify or to identify the errors, and who will access the data, which system need to be accessed data, that will also be taken care by your data link layer. So these are the 5 responsibilities what we had for data link layer. And the next comes, that is the network layer. To be more clear about this topic, after the discussion of these what we say the 7 layers responsibilities, we'll see a video. We'll see a video where it will clearly show how the data will be transmitted over the internet with considering all these things. Right now, what in network layer, these are 2 important responsibilities will be there in network layer. One is called as routing, or we can call it as routing, and another one is called as logical addressing. Now, routing, we had a data, we had everything, the physical entities, physical things is ready, data link is ready. When it comes to network layer, the network layer will take care to route the data from one network to another network. We had many protocols. So which protocol need to be implemented and which is the shortest path to reach the destination, that is all will be taken care by your network layer. That is what the routing means. The second thing, that is a logical addressing. As I said earlier, in the data link layer, every system will have a address called as a physical address, which is nothing but your Ethernet card address or NIC address, which is never changed. That is fixed one, which is written in hexadecimal notation. In the same way, in order to identify system in the network means in your internet, in order to identify a system in an internet, you need something called as an IP address. That is nothing but your logical addressing, where IP address can be changed, but whereas the physical address will be the same all the time. But whereas the logical addressing, that is IP address, can change from time to time. And by the way, and another thing, in physical layer we call the data with the name something called as bits. In data link layer we called it as a frame. Likewise, in network layer we will call the data, call what are the bits as a frame, and the frame when it comes to network layer it is called as a packet. Right? So these are the responsibilities of network layer. And coming to the next layer, that is the transport layer. This is also called core layer of your operating system. Sorry, not operating system, core layer of your OSI model. Now, here I had a very question over here. When you transfer the data from one system to another system, the data will be reached, right? You'll have a file transfer from, let us say, from A system, and you've been sent it to a B. But the thing we need to consider over here is to which process it is delivering the data. The network layer will take care only to transfer the data from one system to another system or from one network to another network. But in order to have a more precise to which process it is being delivered, that will be taken care by your transport layer. So technically we'll call that as a service point addressing, where it has a very specific process to which process you need to send the data, that will be taken care by your transport layer. Now, even though in the video also, if we go back with the video, what he did when you are transferring the data at some point of time, here, not here, I think somehow I missed that. Right, here. Right. If you see the video over here,
in order to avoid congestion together again at the receiver,
what he is doing, let's upload this.
packets, which were put together.
Right. What he did over here, just a minute.
of the lines, the sent files were divided in.
Right. What it did now means, what the data is there that is being divided into parts. If the data is large, if it doesn't fit into the network, if it doesn't fit to our line or the transmission what you're using, what we'll do means we'll divide the data into sub parts. We'll divide the data and we'll send the data across the network, and at the destination what we'll do, we'll assemble that particular data. What are the parts we are divided, that will be unassembled. This will be taken care by your transport layer. This will be taken by your transport layer. That is called as segmentation and reassemble. And I also forgot one more thing. As the data moves from network layer to transport layer, we'll call that as a segment. Right? Now, the next responsibility of the transport layer is connection control. In general, we had two types of connections. One is connection oriented and connectionless. So in transport layer, we had one protocol which is used for connection oriented, that is something called as TCP, and for the wireless, that is connectionless, we use something called as UDP, user datagram protocol and transmission control protocol. So these are the responsibilities of your transport layer. Then coming to session layer, I think I missed the order, if I'm not wrong. Right. The first comes the session layer. Session layer, and then session layer, then presentation layer. Right. Now we'll come back to a session layer. So in session layer, it's very simple. What it will do means it will just establish a sessions, that is the timeout concept for your data to be transmitted. So that is technical term, what we call it as a dialog control. And also it will take care regarding the synchronization of data among the sender and receiver. So these are the simple two things what we had for session layer. And the next comes the presentation layer. The name itself suggests is that the way we present the data. In general, if you take out the languages, some may understand English, some people may know Telugu, some people may know Bengali. Likewise, what it will do means it will translate the data. The presentation layer will translate the data in such a way that the system will understand. Obviously, what the system will understand only the binary data or the signals. To that form, it will be kept translated. And other than this, what it will do, it will also encrypt the data in order to provide certain security. And if the file is large, what it will do, it will also do the compression thing. So these are the three responsibilities of your presentation layer. And the last one, that is something called as an application layer. Previously in transport layer, when we are discussing, in order to be more precise, to which process the data has been delivered, that will be taken care of your transport layer. In order to transfer the data, we need some third party software. It is not just simply just go data. If you say to the computer just go data, it will send the data to the destination. No, we need to have some third party software in order to send the data across the network. For example, if you have a telnet, what we'll do using telnet, we'll transfer the data remotely. Or best example, what we use the team viewer. What we'll do, we'll take the control of other system and we'll transfer the data, or we'll copy our data onto the other's desktop. That is a third party software. So in order to transfer the data, we need to have some third party software. All that services will be taken care by your application layer. So these are the 7 layers what we had in your OSI model, which is responsible to transfer your data. If you see once again the 7 layers what we had, the first one is physical layer, the second one is data link layer, the third one is network layer, then transport, then session, then presentation, and the last one is application. It will be there at the sender side, all the 7 layers, as well as the receiver side. So which layer is directly connected to the thing? That is the physical layer. Now we'll see a small uh, diagram. Actually there is one diagram I had with me. OSI model, right? If you see the diagram, see, so this is a diagram. The first physical layer, we'll call it as a data with something called as frame, and then we'll call it as a frame, sorry, in physical we'll call it a bit in frame, and when we move to the network layer we'll call it as a packet, and move to the transport layer we'll call it as a segments, and in all the 3 layers we'll call that it is the data in session, presentation, and application layer. If you see the functionalities also, it's been clearly given over there. That is the transmission things, it will be taken care, and the data will be transmitted in the sort of frames what is given over here, and it will be network routing will be taken care, reliable transmission will be taken care here, and you're managing sessions and the translation in presentation layer, and the APIs or the directory services what we use in order to transmit the data. And if you see the examples also, here is being clearly given the physical things and what are the Ethernet standards what we use, that is 802.3 standard Ethernet for IEEE, and the IP address. What I said, in order to have identify a system in your network, we need an IP address. For that we have 2 versions, version 4 and version 6, and then the TCP UDP protocol, a remote procedure, and some sort of standards in order to transfer. And these are the services what we use. These are the services what we use in order to transfer the data using applications. So this is about your OSI model, the 7 layers of OSI model. Then comes, after the OSI model, some intelligent people came together and sat and they thought the application, presentation, and session layer are getting wasted. Instead of 3 layers, what they did, they combined these 3 layers as a single layer, and they proposed something called as a TCP/IP layer. So in out and out, at the end, what the TCP/IP model says means it consists of only 5 layers. One is physical, one is data link, the network, transport, and application layer. That is with respect to the OSI model. And if you go to the TCP/IP model, it will be called with a different name that we'll discuss later on. What it will be named, what are the additional responsibilities it will have in TCP/IP model. But whereas in OSI model we had these 7 layers, right? Now, what we'll do, we'll just close this. We'll close this VLC media player also. We'll close this VLC media player also, and we'll see a simple what you say, a video where it demonstrates how the data will be transferred across the internet, right? So here we'll come across with certain additional things, some terminologies like gateway, the protocols, and all these things that we'll all discuss later. We'll discuss in the next class. But as of time being, what in this video we'll see what are the different things we need in order to have a communication or transfer data across the internet, and how it will participate, and how the communication originally happens in your internet. That is a demonstration of video over here. We'll see that. So these are the star cast. What it is showing is a star cast of this particular short film.
For the first time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. The highway of the LAN is packed with all types of information. These are IP packets, Novell packets, Apple Talk packets. They're going against traffic as usual. The local router reads the address and, if necessary, lifts the packet onto another network. The router, a symbol of control in a seemingly disorganized world.
Whoops, sorry about that, Pop. This one here, this one here. Oh, this one goes here, this one goes here. I don't like this one. Let's show this one. Let's go here. Pop a little bit. Let's put this one here. Another jack here. Let's put that one here. Let's put that one. Let's put that one here.
There he is, systematic, uncaring, methodical, conservative, and sometimes not quite up to speed.
Sorry.
But at least he is exact, for the most part.
That's what I'm going to do. Was there, and this one was there. Oh, another one was there. It was there. He's going to there. It was there. It was there.
As the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will.
Here we go. Here comes another one. And it's another. Watch this, Mom. Here goes. Whoop, around the back. Hey, in there, in there, in there. Over the left, over the right, over the left, over the right. You got it. Here it comes. Right out. He shoots. Heat stars. It's going. Hey, wait. Hey, watch out. Here comes another one. Oh, here we go.
As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address, or URL. Depending upon whether the address is acceptable, the packet is sent on to the internet. There are, however, some addresses which do not meet with the approval of the proxy. That is, next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We are now ready to enter the world of the internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your LAN. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The path our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat. Literally. And all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall could be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while port 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. The firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet.
It's okay, go on. It's okay. No problem. Have a nice day. We out here. Bye.
For those packets lucky enough to make it this far, the journey is almost over. It's just a lineup on the interface to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk. Why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. One by one, the packets are received, opened, and unpacked. The information they contain, that is, your request for information, is sent onto the web server application. The packet itself is recycled, ready to be used again, and filled with your requested information. Addressed and sent out on its way back to you. Back past the firewall, routers, and on through to the internet. Back through your corporate firewall. And onto your interface. Ready to supply your web browser with the information you requested. That is, this film. Pleased with their efforts and trusting in a better world, our trusty data packets ride off blissfully.
So hope you had enjoyed the video. It clearly shows how the data is transmitted over the internet, with considering all the routers, switches, gateway, and all these things. So that's all for today's class. Hope you people understood that. In the next class, we'll see what is the advantages of TCP/IP model and how it works. We'll see in the next class. Thank you.